Let's start with our webinar about temperature modulated DSC measurements. So especially I want to tell you a bit more about our chip DSC here. Um, however, that's me. I'm Michael from Linseis, and yeah, if you want to contact me, you're welcome to find me on LinkedIn, write me a mail, or of course, give me a call here. So I'm responsible for the chip DSC here, especially, and yeah, this is Linseis. So Linseis Thermal Analysis manufactures instruments for thermal analysis and the determination of thermal physical properties, of course. So we're a family-owned company that was founded in 1957, and yeah, our headquarters is here in Germany, but there are subsidiaries in USA and China, and yeah, but we're acting all around the world. So if you want to buy an instrument from us, I think you will find a way to do that. Yeah, so this is our product range. So I think we have a quite broad product range for thermal analysis here. So today, of course, we want to talk about differential scanning calorimeters, but there's also STA, stellitometry, thin film analysis, and so on. So there are many instruments, but today, as I already mentioned, we want to talk about DSC that was invented before about 70 years. And yeah, the special thing about the system I want to talk about today is the measurement cell here. So with the chip DSC, we've changed the measurement cell a bit. So here on the left, you can see the classic layout for DSC. So you have a surrounding oven with the heater, of course, and inside this oven you can find a sample crucible and also a reference crucible with the thermocouples. And yeah, we've changed the layout to a vertical way. So of course, at the top is still our crucible with the sample inside, and below you will find the temperature sensor for the sample. In the mid of our sensor, you will find the heater, so there's no more surrounding oven anymore. And below that, you will find the temperature sensor for the reference, and at the bottom, the fixed reference here. So everything is inside of one ceramic monolith, and this monolith contains all parts you need for a DSC measurement here. So, yeah, there are some advantages through this, because what you can see here at the bottom is our smallest device here, the chip DSC1 or chip DSC10 with a footprint of 20 per 20 centimeters. So it's quite a tiny device, but of course there's also a bigger version with much more options. You can see here at the bottom also. So there's the possibility for a sample robot. There are Raman spectrometers, cameras, UV light options, different cooling options, and many more. So basically, I think we can cover many options here with these devices, but especially in smaller labs, it could be quite helpful if you have a smaller device here, because the sensitivity and the possibilities for conventional measurements, conventional DSC measurements, are the same here. So there's also a cooling option for the chip DSC10. However, sometimes size matters, so of course there's also the big version. The sensor you can see at the bottom left corner here, so it's quite a small measurement system here. And yep, so it could be changed by the user itself. So you just need 20 up to 25 minutes for calibration. This depends on the conditions you want to choose, so the heating rate and the materials, of course. And yeah, so I think it's a smart thing here. But let's talk about the DSC measurement itself here. So here you can see a conventional DSC measurement. So where do we use DSC in industry, teaching, research, and wherever? So for identification for polymers, or just to test, okay, what about my food, and so on. And what we could get from these measurements, you can see at the example here at the right. So that's a heating and cooling scan of a polymer. And what we can see there is a glass transition at the heating run with the hysteresis peak or a relaxation peak. And the next thing is the exothermal coat crystallization. Then, of course, the melting of the polymer. And then you can choose with or without oxidation, the oxidation itself, or the decomposition, the thermal degradation. And also on the cooling scan, we can see some things. Of course, when something melts, we can see also the crystallization here. And also the glass transition could be seen here at the bottom at the cooling run. So these are the enthalpic transitions we could get from our DSC. But what we also can see here on this slide is there are some overlapping transitions, like the glass transition and the relaxation or the hysteresis peak. So they are overlapping. So it could be hard to get some valuable results from here. So this is what we talk about today. But at first, the main thing we want to achieve with our temperature modulation is the CP, the specific heat capacity. And so it's defined as the specific heat of a substance is the amount of energy that must be added, taken up, to heat one unit of mass of the substance for 1 unit in temperature. So the unit for CP is joule per gram Kelvin. And so if you don't know, what is this especially? So it's the energy, for example, to raise the temperature of 1 liter water by 1 Kelvin. So this is how we get the CP here. This is the CP, this required heat to raise the temperature. So there's the CP for the DSC measurement, but this means the pressure in this system is constant. But there's also another option, so it's the CV. That means the heat capacity with a constant volume. But with DSC, we just make sure our pressure is always constant, because this is important for the DSC measurement itself. So that's it for that slide. Let's come to some other important things. Of course, the CP is temperature dependent. Otherwise, it doesn't make sense to heat it up with the DSC, I think. And itself is defined by the molecular structure of the material. And yeah, CP and also CV with constant volume describe the heat capacity under different thermodynamic conditions. An important thing we will focus later on also is the CP during a phase transition, like the melting or crystallization is defined as infinite. So we cannot say, okay, the CP in this melt is 3 joule per gram Kelvin or something like this. That would be important later, I think. And what's also important, CP is often hard to measure at really high temperatures. Here, the infrared irradiation is the main thing for the heat transfer, and not the heat transfer between the sample crucible and the measurement system anymore. So it's hard to detect here valuable CP values, but the most DSCs, or the standard DSCs, are limited to 600. So it doesn't matter here, but of course also at 600 or 700 degrees it has an influence here. Well, there are some different ways to determine the CP with some calorimetric devices. So there's the classic method, the temperature modulation we want to focus today, and also the free omega method. And of course, we measure with DSCs here or with calorimeters, and so all of these methods assume a defined heat flow to the sample. So that's the main important thing, because basically this is what we can measure with a DSC here. And also what's a must here is the calibration for the CP. So we need a reference material whenever you do this calibration, before the measurement or if you set up the device, we have to calibrate the CP through the tolerance of the measurement system itself. So the classic method is, I think the oldest and the easiest way to measure CP with DSCs. So basically, we need 3 steps here to receive the CP results. So at first, we need the zero curve. So this is just the crucible in the measurement system without any sample or reference material, whatever. So this is important to get some information about the measurement system itself. Under the same conditions, we can measure then the calibration. So we have to determine the calibration factor for the CP measurement, and so we need to heat up any reference and calibration material here. For example, often we use sapphire. And last but not least, of course, important is here the sample measurement. So of course, we want to determine the CP for our investigation. So what's important here for these 3 measurements is we need identical ambient conditions and parameters. So we need the same heating rate, in the best case, the same temperature range, and also the same atmosphere, and so on, the same crucible. This is pretty important here. So the zero curve will be subtracted from the calibration and the sample measurement, and then we can calculate the calibration factor. So what are we looking here? So we've got these 2 measurements with the correction measurement. And so we look here at the offset and the phase shift of our measurements. And this is how we receive our CP. Here you can see on the right now the temperature profile at the bottom on the B. So we are checking the rise time here. And above you can see the 3 measurements you need. So at the bottom you can see the empty pan, so without anything inside, just the measurement cell and the pan. And a bit higher you can see the calibration substance and the sample. So what we already can see here is the heat capacity. So is higher in this case for this specific sample with this amount. So with this mass is higher than the calibration substance. Yeah, so that's it for the classic method, but let's talk about the temperature modulation way. So here we enable the acquisition of some additional informations in comparison to the conventional DSC measurement. So we don't heat up anymore in a straight way, but we have a sign here on our measurement. So we have small amplitudes over our main temperature raise. And you can see here the conventional measurement in a black line at the upper part of this diagram. And the red one is the temperature modulated way. At the bottom, you can see an example here. In this case, it's PET with the glass transition, the recrystallization and the melting in a raw curve. So for a conventional measurement, and the red one, the red curve here is the temperature modulated way. So this looks a bit curious here, but we will get some information through this. What we also already can see here is after the glass point, for example, the amplitudes of our results are higher. And also in the melt, the amplitude gets really high. So this is now a literature value for a CP of a polymer. And what could we see here for the CP? Okay, it's rising. And then there's a small step at around about 70 up to 80 degrees. Then it's still rising, and then we have the peak here. I think it's the melting peak, so I can tell you this is the melting peak. And then it goes on at a bit lower level here, but then it will rise again. So, okay, this is the literature. But there's some more information we could get through the temperature modulation. So this is the reversing and non-reversing part of our measurement. So here in the mid of this diagram, you can see the total heat flow of, for example, PET. I think it's PET here. So we can see the glass transition at around about 80 degrees, the recrystallization at around about 130 till 50, and the melting at around about 250 degrees. And now we can split this signal to the reversing heat flow at the bottom and the non-reversing heat flow at the top here in this diagram. If you remember on the last slide, it looks almost like the reversing heat flow. Let me go back. Okay, this is the reversing heat flow flipped upside down, and that's totally right. So the reversing heat flow is the reverse of our CP signal. So also here we can see our glass transition and the melt. And what does this say? Okay, the glass transition and the melting is a reversing transition here. So it doesn't matter if you heat it up twice, 3 times, whatever, you will always see this glass transition and the melt here. But what about the rest? So the non-reversing heat flow, of course, we could see here the recrystallization, but there's a second transition here in the range of our melt. And we cannot see this in the total heat flow, but if we check the reversing heat flow and the non-reversing heat flow, in the reversing heat flow, the melting peak looks much bigger than in the total heat flow. So this melting peak is overlaid by a second exothermal reaction here, and this is what we just can these information we just can get through this temperature modulation. Okay, let's come to some theoretic things. At the top we can see here our conventional measurement. So this is the temperature, dependent on the time, of course, is our start temperature plus the heating rate multiplied with the time. Okay, so far so good. That's the easy way. But now we are looking at the temperature modulated way. So here we add the amplitude AT of our temperature modulation, for example, 1 Kelvin or something like this, multiplied with the sine omega, and of course we need also the time here because everything we measure is time dependent in this case, time and temperature dependent. By the way, the omega here is of course the period of our modulation, important to know. So okay, through this temperature modulation we could get some results. I've checked it with our chip DSC and the results are quite good. So what I've tested here is just the zero curve you can see here in blue at the bottom of this diagram, and then also the calibration curve and the measurement curve. So basically both of these materials are sapphire, so they are basically the same. And then I do the evaluation for the CP, and at the upper part of this diagram, you can see in black the literature value for sapphire. And then in blue, we can see the result of another sapphire, and the variation here, the biggest variation is 1.5%. So, yep, this looks pretty good here. And so with the chip DSC, we could get, or through the temperature modulation, we could get accuracy of round about 1 to 5% error here. So that's a good thing for a DSC. If you remember, we are measuring around about 25 or 20 milligrams of our sample here. And what we also can see is the amplitude is directly dependent on the specific heat here. But maybe we've got another example where I can explain this here. Okay, normally we should choose a calibration material that's almost similar to our sample. So if you measure, for example, a metal, you should calibrate with a metal and not with a polymer, because the heat capacity and mostly also the weight are really different here. But I want to check that if it's still possible with the chip DSC and temperature modulation to get valuable CP values here if I measure some metals. So I've tested this with indium, and this was just one shot. So I've measured the indium 3 times, and what you can see here are 2 measurements of this indium. And what we can see here, the reproducibility is quite good. So behind this black CP value, there's also a red one. Maybe you can see it, I'm not sure. So they are really similar. And what's also interesting and makes me quite happy, because I'm the engineer who is responsible for that, is we hit exactly the literature value. So the literature says it's 0.23 joule per gram Kelvin, and this is exactly what we can see here. So what we also can see, of course, is the melting at normally 156.6 degrees Celsius. And as I already mentioned, the CP isn't defined in this transition, because if the measurement system has to bring more heat into the sample to follow the temperature profile. And for this reason, it looks like there's a bigger CP, a bigger heat capacity for the measurement system, but of course it's just the endothermic effect of the melting here. So for this reason, we cannot define the CP during the melt. But what we can look is behind this melt. So we will realize the value for the CP there is a bit lower, but also this is possible for materials. The CP of a liquid is lower than the solid before melting. Okay, another test was here to figure out the amount of water and the CP of the rest of the substances that are inside this solution. And so the customer asked for a specific heat run for his liquid sample. And what we can see here is also the light blue curve is the correction curve, and the green one is the sapphire calibration curve. And in red, you can see here the customer sample raw data. And what we also can see here is the amplitude of this signal gets lower and lower until 23 minutes. And also, if we evaluate this signal, we will see, okay, the CP gets lower here. Of course, the CP of the material inside isn't lower, but the CP, the chip DSC or the device itself sees, is lower because the water evaporates. And so there's no heat needed to heat it up because it's gone. And but basically this was the customer want to see, so he wasn't interested in the difference. Of course, if you want to get the CP of the part when the water is gone, then you have to weight this crucible again, and then you can calculate the CP behind the evaporation of the water. However, it's also possible to see the CP of a liquid, but keep in mind it will maybe it will evaporate. Okay, now here's again an example from myself, and yeah, I hope you also can see this is the same result than the literature CP value before. And yeah, what can we see here? The CP increases with the glass point at around about 75 degrees, so 70 to 80 normally for PET. And yeah, there's no recrystallization because it's non-reversible. And then we will find the big melting peak. And of course, this correlates with the amplitude of our signal, of our raw signal below. During the glass transition, the amplitude gets higher. At the recrystallization, we can see at the raw signal, the amplitude is constant. And for this reason, we cannot see it on the CP signal. And then during the melt, of course, there's much heat needed to heat the sample up. So here, the amplitudes are extremely high. And later, it's lower again. And also on the CP signal, we can see here the CP of the liquid is lower than the solid before. And then, of course, I have to validate my measurement system and also give some hints to the customers and also for myself, of course, for our measurements here in the lab. What are the best conditions for this measurement system? So I've measured the same sapphire sometimes, and then I've checked, okay, what result is here the best? And what you can see, the deviation could be pretty big here, especially at the light green measurement. That's totally wrong here. Yeah, and so the result is the gray line, by the way, is the literature. And yeah, with the purple and the blue, we hit the literature values pretty good. But yeah, the faster we've got, the lower our omega is, so the period. Yeah, the worse the result will be. So there are some optimum settings here. Mostly I use 60 seconds period and an amplitude of round about 1 Kelvin, sometimes 0.5, sometimes 2 Kelvin or something like this. But yeah, this will lead to the best results here for this heating rate and this sample. Of course, this is also important to check what's my heating rate. If you, for example, heat with 5 Kelvin per minute, yeah, it would be possible to choose a lower period and or maybe a higher amplitude or something like this. This depends on your needs and of course also on your sample. And yeah, that's it here. So this is normally my recommendation. We use mostly in the first try 60 seconds period and an amplitude of 1 Kelvin at 10 Kelvin heating rate and mostly also at 5. So this is a good setting. And what's also important is the sampling interval for our amplitudes. So there are some different options we have here in our software. Of course, you can also just smooth the result, but also you can choose a different sampling interval directly in the file system of our software. And so what we can see here with, for example, one sample per period, there isn't a really sharp glass transition, and also the melting peak isn't really sharp. But what we can see here is there's almost no noise. So if you're just interested in the measurement of, yeah, without any glass transitions or transitions at all, then it's totally okay to choose less samples per period, so a lower sample interval. But if you're interested in the glass transition or something like this, then you should choose a higher sampling period here. As you can see, the glass transition with the gray gray measurement here. By the way, it's the same measurement, but it's much sharper here. Another investigation was the choose of the right sample mass, because also this would affect our result here. And so I've checked, okay, let's choose something between 25 and 50 milligrams. And what we can see here is, okay, the deviation is around about 3% error. But it is important. So the heat capacity of your sample, the heat conductivity, and really important is the shape of your sample. So this will affect the accuracy of your result here. So because it's really important, the heat could go through the crucible into the sample. So for this reason, the shape is pretty important here. And also, if the sample is too high, for example, if you use a polymer granule with bad heat conductivity, and it's, for example, 10 millimeters high, then you will receive a temperature gradient. But this I can show you on the next slide here, I think, especially here. I've measured some different alumina samples. So there is the sapphire literature value here in this diagram, and I've measured against this sapphire and powder. So these are the upper curves with a big deviation here, and also with a plate of alumina. So alumina and sapphire, basically it's the same material, of course. Sapphire is just one big crystal of alumina. But yeah, the specific heat capacity is basically the same. And this is what we can see here. A plate with a good shape at the bottom works much better than powder, because between the powder particles here, there's many air, and so the heat transfer is pretty poor. So also the shape and the condition of your sample is quite important for your investigation then. I already mentioned there's some more information than CP we can receive with the temperature modulation. So here's the example again for PET with the reversing and the non-reversing heat flow. So at the top we can see the CP signal. We already discussed this before, and in a bit you can see then the reversing heat flow. So that's the CP upside down, and the non-reversing heat flow with the recrystallization and this second crystal perfection there in the range of the melt. And what we also can see in the range of the glass transition there at around about 8 or 9 minutes, there's some small endothermic peak at the non-reversing part. And this is this hysteresis peak I was talking about. And so with this, with splitting the DSC signal, we could see this hysteresis peak without the glass transition, and the glass transition without this hysteresis peak, because this peak is non-reversible, so it wouldn't occur again under normal conditions. Of course, if you quench the sample or something like this, it's possible to receive this again, but the character of this small endothermic peak is non-reversible. And at the bottom, you can see the total heat flow, and again, the raw signal of this measurement. So again, some theoretics. The total heat flow is the reversing heat flow plus the non-reversing heat flow. And so the non-reversing heat flow is the total heat flow minus the CP multiplied with the heating rate, and the reversing heat flow is the calibration factor multiplied with the amplitude multiplied with omega, the cosinus of omega and time, and of course the CP here. So this is how we get the value of the CP. So basically, the CP is defined as the amplitude of my DSC signal. You can see here at the gray measurement divided by the calibration factor multiplied with my period, so omega, multiplied with the amplitude of my temperature. This is how we receive the values for the CP and also for the reversing and non-reversing heat flow. Yep, I think I already discussed it with you a slide ago. So yeah, there are some things we need for these measurements. So the most important thing is the sample must be able to follow the temperature profile. So especially at lower temperatures near room temperature, or if you use a low temperature option near the lowest possible temperature, it could be hard to cool down because the temperature gradient is pretty small here. So for this reason, the first period and because it's not a complete period, also the last period of a measurement could be a bit strange. You should ignore them. By the way, in our software, it's cut it away automatically, so you don't have to mind about things. What's also important is the good sample contact, otherwise you cannot get the heat into the sample, and the limited sample volume to avoid temperature gradient. So our standard crucibles for the chip DSC, for example, I think the biggest crucible is around about 100 microliters. So everything is okay then. But if you calibrate with a 0.5 millimeters calibration material and want to measure a 5 millimeters or 10 millimeters sample, for example, polymer with bad heat conductivity, then there will be an error. And so this is what you have to make sure this doesn't happen. And of course, a simple thing, the sample must not react with the crucible material. So I think that's clear. If you want to measure gallium, yeah, we need some different crucibles than our standard crucibles made from aluminum. Of course, you can use alumina, you can yeah, use whatever crucible you can find here. And the general procedure is, at first we need the correction curve, we need the calibration curve, mostly made with a sapphire, and of course we want to measure our unknown sample. So now I want to show this on our software and the evaluation, because I think this could be important for those who already use a Linseis device or especially a chip DSC. So let me show you the chip DSC software. So by the way, our software is split into 3 parts. So at first we have the measurement software you can see here for the chip DSC, and we have evaluation software and the administration software. At administration, you can set up your devices, you can set up your literature or reference materials, and also you can define the users. In the evaluation, clear, you can evaluate your measurements and so on. By the way, with every Linseis device, you can use a dilatometer, you can use a TGA, you can use a DSC, and you can combine these evaluations in one program. And yeah, last but not least, here our measurement software. And yeah, now I just want to show you what we have to insert here. I don't want to do the complete measurement because this will take a while, but I think, yeah, so a short hands-on for those who want to use this function is pretty good. And yeah, of course, we need the name for our measurement. So let's call it correction measurement. With the correction, the weight doesn't matter, because so for this reason, 0 milligram or for example 1 milligram, it doesn't matter. The software ignores that for the correction measurement. So then the sampling interval 0.1 second is quite okay. We have no customer, this is my folder, and there's no order number. But what we have to change is we want to do a correction measurement. And now we all already can see here, we are not allowed to choose any correction curve anymore. And this is what's important. Please if you want to measure with temperature modulation and chip DSC, don't use any correction curve. This is what the software is doing by itself, so there's no need for any correction curve here. And yeah, what we have to set up is our temperature modulation. So normally, yeah, in many cases, I'm using 60 seconds period and 1 Kelvin amplitude, and then we can choose our temperature profile. Common practice is here something like 10, 5, or 15 Kelvin per minute. This depends on the temperature range. If you just want to measure until 150 degrees, I would recommend 5 Kelvin because yeah, we need enough amplitudes in our measurement here. So for this reason, and it's limited, and of course also the sample has to follow the temperature profile. So also here the heating rate is a bit limited. Normally conventional DSC degrees. This depends on the transition where we want to check. But yeah, so this is a K value. So this will take around about 29 minutes. And then what I also I'm doing for correction curves and calibration curves, I use a scheduler. So I just tell the software, run this measurement 3 times until you reach a temperature, for example, of 30 degrees Celsius. So the software automatically starts again at 30 degrees Celsius. And this is what I'm doing 3 times because so I can make was gone into the lab or something like this, or there's some radiation through sunlight, or yeah, things like this that could affect our measurement. Yeah, for this reason, I'm using the scheduler, and then I can click start, and that's it. So of course, I would like to stop this measurement and go on with the calibration. So what we have to change here is, of course, the name. Let's call it calibration. And now we have to insert the right value very precisely. For example, it's a 24 milligram sapphire or a 24.59 milligram sapphire. And we have to change it here to a calibration measurement. And now you can choose here the material you want to use. The preset is sapphire because this is what we normally deliver. But of course, you can use your own material if you have the literature values here, or one of our material from our database here. And then that's everything we have to change, because temperature profile and temperature modulation must be the same. And so also here, we can go on with the measurement if the correction stopped. And last but not least, we want to measure our sample. And also here, of course, we have to adjust the name and the weight. So for example, it's 30.1 milligram. And now we can choose here the sample measurement. So there's no literature value because we don't know what we want to measure mostly. And then also that's it. We don't change temperature modulation. We don't change the temperature profile. We also don't change the gas profile if there is any gas profile. And then we can start the scheduler again, and that's it. And if we finished, it will look like this. So here we have now our correction measurement, the red measurement. In blue, we can see the sapphire, and in black, we can see the sample. Maybe you remember this could be PET. And yeah, what do we have to do now? We want to create a calibration here. So this is our evaluation software. You can load all your measurements if you, so it depends on you how to organize your measurements here. And yeah, there's the modulation button. So the modulated evaluation separates the reversible and non-reversible parts of a modulated DSC curve and calculates CP. So now I want to create a calibration, and now I have to check for the right curve here. I think I've called it something like modulated. Let's search for it. And yeah, this is the right measurement here. Yes. And now he is asking for, do you want to create a calibration? Yes, I want to. And this is my CP calibration for a webinar. Okay. So what can we do else with this calibration measurement? We can create our literature value here. So we can choose this tool again. We have to choose the right correction curve. And now we don't want to create a calibration. No, we want to use our latest CP calibration, and this is our result. Now we can split it here, and this is the result for Sapphire. We can also plot the literature value by itself. So here we can see it over a temperature range. Let's create a curve, and of course recalibrate it for the Sapphire, so it must be the same. So it's 100% the same. But the interesting thing is our sample, of course. So also we have to select the measurement we want to have a look on. And now we use the modulation button. We have to choose the same correction curve. Sorry. Let's try again. Select it. And now we have to select the calibration we want to use. And now we can zoom out and see, okay, this is my CP value. So let's try again here in the bigger view. So also here we can see the TG and also the melting, and which we can see here the sampling interval was pretty high. So it was about 32 or 64, something like this. So what we already can see here at these extreme points is the modulation. So in this case, if we are interested in such a huge rise of my CP, please keep in mind it's not defined here in this range. Then we have to choose a slower, a smaller, rate for the sampling. So basically, that's it. This is how our software works here. So basically, that's also from my side. And now let's go for the discussion. And yeah, if you have any questions, you're welcome to ask them. Yeah, the first one's here. Could you tell or show me how to calculate enthalpy of relaxation by means of modulated DSC? Example of separating TG reversing signal and non-reversing signal. Okay, so you want to see the enthalpy of the relaxation during a glass transition, all right? So we can see if it's on this measurement here. I'm not really sure, but we can duplicate here for the non-reversible part. And yeah, in this case, it wouldn't be so big. Let's try. Yeah, here this small part is the relaxation, so it's pretty small. We have to zoom in here, and now we can have a look on this. It's that small part, and now we can choose our peak evaluation. Come here, this display is too small. And this is then the enthalpy for our relaxation. So you have to right click on your CP signal, then you can duplicate it. You can choose, do you want to see the CP, the average, so the total heat flow, the non-reversing or the reversible heat flow, and then you can evaluate it like a normal signal, a normal heat flow signal here. By the way, if it's necessary for someone, of course, it's also possible to export these files on a table or a diagram as a picture or PDF or whatever. And of course, it's also possible to import any CSV files or Excel files or something like this. So that's also comparable. Okay. Yeah. Are there some other questions? You're welcome. If you have any further questions about to use this device, don't hesitate to ask me, to write me a mail or to find me on LinkedIn. And yeah, this is also not a problem. Okay, if you don't have any questions, then we already finished for today. But it's up to you. Of course, I can wait a minute or something like this. Many thanks. I'm happy to find you here for all participants. And yeah, that's the chip DSC. This is what we can achieve through temperature modulation. And many thanks for your attention. If you want to, you can contact us here at Linseis or me directly through my mail.